All right, guys, welcome back. 13, 4, 5, and 6 this week. Going to wrap up chapter 13, which we started with all the sequences and learned about some different patterns in order to figure out what is the next term on the list. Well, now we're going to talk about a series. All right. Now, we talked about arithmetic and geometric sequences and how arithmetic uses arithmetic to move from one to the next, either adding or subtracting by some common difference, and geometric was multiplying by some ratio. Now we can say ratio because if we wanted to divide and it was being cut in half each time, then rather than saying divide by 2, we can say multiply by 1/2, and that would be the ratio. So for this section, we're going to be talking about a series and what that is. So what do you think a series is?
It's a list of numbers.
Now, careful, that's what a sequence is. A sequence is a list of numbers. So if I give you a sequence of things to do, then that would be like a list. Where if you ever watch baseball, they call it the World Series for the championship. And in order to win the World Series, what do you have to do?
Win.
How many times?
Uh,
You're like, I don't know, I don't watch baseball.
yeah.
But no, it's not just one time, right? To win the World Series, you have to win 4 out of 7. So it's the sum of wins, not just a win, right? It's not like in the NCAA basketball tournament where you just have to win a game and then you play another one and you win that one, right? It's a series of wins. So we're going to say the term that we use in math is a sum when you add up a bunch of things. Okay? And in this case, it's the terms or numbers of a sequence. Okay? And we're going to talk about 2 different types of series or sums. One is going to be what is called a, how do we say that?
Finite.
Finite, meaning what?
It stops at some point.
That's right. It ends, it has an ending term. Okay? And that is what is going to be called the nth partial sum, where the nth is going to represent how many terms. Sum, obviously, that you want me to add up, and partial meaning it's not the entire sequence. It's just these. Okay? So that's what they mean by nth partial sum. If you want just the 10 first terms or the 15 first terms, then that's what we mean by nth partial sum. But of course, if there's finite, then there's not finite, which means it doesn't end. And what do we put in front of that to mean not ending?
In.
IN.
That's right. IN. Infinite or infinite. Wait a minute. Let's think about that. What does that mean? And I tried to give you, wait for it. We're going to find the sum of a infinite series? What does infinite mean?
Goes on forever.
So how are we going to add up a bunch of numbers that never end? Cue mind blown emoji. So I wanted you guys to just think how and when that might be possible. Any thoughts that you guys might have on when we might be able to do that? All right, I gave you a second to think about it. I stopped the recording. Anybody think how that might be possible?
Does it have to do with how it approaches 0 or 1?
Now, 0 or 1, if I kept adding 1 a bunch of times, what's going to happen to that number?
It grows.
It grows not by much, but by 1, but it still gets bigger and bigger and bigger and bigger. And if this never ends, we put the dot, 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 then we know it's going to approach. Remember when we talked about that a couple units ago? It would approach the symbol we made up for as big as we can think of, infinity. And again, whether it's positive or negatives, then we just put a negative on there. So Brianna, you're absolutely right about the 0. Because what would happen if it just kept getting smaller and smaller and smaller and smaller? Eventually, when we add something that is approaching the smallest number we know, and you're like, whoa, whoa, what about the negatives? Those are smaller. Yeah, but that's the wrong side. That just means it's negative numbers. They still get larger, but on the negative or left side of 0. 0 is the smallest thing. It represents nothing. So if we add something that's just getting smaller and smaller and smaller to eventually say it's approaching nothing, then what happens when we add nothing?
You get the initial value?
That's right, we get that same thing out. Very good. So yes, there is going to be a caveat for us to actually be able to find the sum of an infinite, what we call series. And we're going to have some symbols to denote what these things are. All right. So a series, which we're going to be representing not a list anymore like a sequence, but a sum, is typically denoted with a capital S. Now that's confusing because both sequences and series start with capital S. Okay. But this is going to represent the series or the sum. And we're going to use both the English capital S and the Greek capital S. And does anybody know what that is?
Sigma?
Very good. It is called sigma for all of you that are pledging. If you look across the street at Shaw over there next to our university, you'll see a bunch of these Greek letters because that's where a lot of the fraternities and sororities are, and they use Greek letters to represent that. Okay, sigma is like a big uppercase E. But instead of being straight on the end, it actually goes in instead of just being like this. Okay, so this and this mean that we want to find this. All right, so this form that we're talking about here is called summation notation. Notice the root word there is what?
Sum.
Some.
That's right. Some of you figured that out. Very good. So what we're going to have to know in order to find the sum using that sigma is how do I find all of the different parts, right? Those rules that we talked about to find any term, they're going to give us that formula. And then they're going to tell us, where do you want to start? All right, let's say at the first term. And then where do you want me to end? And you guys know in life, you got to start at the bottom and work your way to the top. So we're going to have that same thing here. So they're going to give us the formula and put it right in front. Find the sum of all of these things that behave this way. start at the first term and then add up all the way up to the what?
Nth
Fifth term. Okay, so that's what we're going to be doing for these. Again, that is called summation notation when they have the Greek letter S called sigma. All right, so there it is. If you guys want to put any of that down for your notes, and remember, this is just going to be how we find each and every one from whatever they put on the bottom. We call it that lower limit all the way to the upper. And sometimes we just have to use brute force. We have to plug in 1, find the first term, plug in 2, find the second, the third, the fourth, the fifth, and then add them all up. Other times, we're going to recognize that formula is either arithmetic or geometric. And if it is, then guess what they're also going to have for us? A formula to find the sum quickly. If they're these. If they are not, or you're not sure, then you're stuck with having to plug in each and every one, starting from the bottom all the way to the top, and then adding them all up. So there was this guy. He was actually a boy at the time, about 7 years old. His name was Carl, oftentimes goes by Frederick Gauss. And at the age of 7, his teacher told him and the rest of the class to add the numbers 1 to 100. And a few minutes later, he came walking up with the answer. If I asked you guys to do that, what would you all whip out? Trusty calculator. And that calculator would not be able to be used back when he discovered this. There was no such thing back then. So what he was able to do, instead of all of his classmates sitting there trying to add all these things up, he said, you know what? I want to find a better way. Can you guys all see that?
Mhm.
And what he discovered, this 7-year-old boy, was a pattern. And not just any old pattern that you guys obviously see adding 1 each time to get from one to the next. He said, well, if I want to find the sum of all of these, you know what? I'm going to start with the ends. And I'm going to add those two together. Because what does that give me?
101.
101.
Dalmatians, that's right.
Oh.
Now, if I have 101, look what happens when I add the next two things. What am I going to have?
101.
Look at the next two things.
101. Wow.
Yeah, pretty. I mean, 7 years old. Now, this kid was a kid prodigy. He went on to do many, many things in mathematics. But help me out. Just because he found that pattern, what else did he have to figure out? How many times? Very good. Go ahead, Brianna.
How many terms are in the sequence?
And how many are in there total? If we start at 1 and go to 100.
100.
Yeah, good. This would be first term, second term, third term, all the way to the 100th term. And if he saw this pattern and he paired them all up, then how many times would he have 101?
101 times.
Careful.
100 times. Sorry.
50. Wouldn't
Yeah, it would be 50. How come?
Ooh.
he? Because he's taking pairs.
He's taking 2 at a time to
Yeah.
get that 101 that he found. So we'd end up having half of the 100 because we're pairing them up. And all he had to do was take this and multiply 5 to the 1, to the 0, and to the other one. And he walked up there and said, "Here you go, teach. Give me something more challenging." Pretty amazing, 7 years old, right? Pretty neat. But that's what a lot of mathematics is about, is finding patterns so that we can get to the end result quicker. And so what he came up with was this formula. But it only works, if you can see this here, for an arithmetic series. And notice this is arithmetic because what does it do to get from one to the next?
Adds the same value. of
That
the-
same common difference, we called it. Very good. So what this is saying you need to know is your first term, and you will add it to your last term because we're trying to find the sum of this many numbers. So if you know your first term and your last term, you add them together, which is the 101. You take the number of terms that we have, which we said, Jonathan, there was a total of 100 of them, and we cut it in half. So that is where this formula came from. But again, only works, this shortcut, this formula, only works when it's arithmetic. So of course, people wanted to know, well, what would it be if it's geometric? And as you can imagine, it's a little bit more challenging. Okay, no fun story behind it. But this one, you only need the first term, the common ratio between each to get from one to the next to the next. But of course, a little bit uglier, more challenging that we're going to have to deal with. Okay, now notice it does have a caveat that r cannot be 1 because otherwise you get a 0 in the denominator. Also recognize that the n is on the r for that exponent. It is not on the outside of 1 minus r. Okay, so this one is going to be more challenging because what does r stand for?
The common ratio.
Common ratio, that's right. Which means this and this are going to be fractions in our big fraction. So we'll have to deal with some stuff that we've already dealt with in the past. Okay, but don't forget, I did tell you that we're going to find an infinite sum or series. And as Brianna and a few others came up with, when would it be possible? What is required? Well, that it gets smaller. Our sequence, our list of numbers gets smaller and smaller and smaller as we go, because then it's going to get so small eventually that you're not even going to notice that you're adding anything. So our requirement for this, now remember, this is just for an infinite geometric series. Our r has to be between -1 and 1. In other words, r has to be a fraction. That's less than 1. And I add in the less than 1 because 3 halves, if that was our r, what is that actually?
1.5.
Yeah. So it's going to grow by 50% or half each time. So even though it's a fraction, you got to be careful. That would not work, because it'd actually be getting bigger, which means it would actually go to infinity rather than very small number like 0. Okay, so here's the formula for it. which I want to keep both on there. Here was our geometric, but notice, look how much easier, which is weird because we're adding an infinite amount of numbers. Notice that is still there, but this is the formula, which is actually way easier than this. But remember the difference? This is for a finite geometric series, where this one down here is for infinite or infinite. So all you need to know is A1 and R. Notice it's missing the ends like this one had, because we're not finding a certain number of them, we're finding all of it. So to help you kind of visualize what we're dealing with here, I wanted to give you a quick example to show you how this works. Now, I'm not going to do it with the actual formula just yet. I want to make sure that you guys understand why this works. For example, could you find the next couple of terms for me? Can you find the common ratio?
It's 1/2, no?
Yes, very good, it is. Half of 8 is 4, half of 4 is 2, 1 half. 1/2 of that is 1/4. What's half of that?
1/8.
Good. Half of that,
1/16.
and so on. Good. Now, of course, instead of commas, what should I be putting in between?
Adding.
The sign.
We are adding them. That's right. So, couldn't you add some of this right away? Couldn't you add the 8 and the 2 to get 10? And the 4 and the 1 to get 5? And even the 1/2? Couldn't we do that really easily on our own? What is our sum so far?
15.5.
15.5. But now I need to add the next term, which would be 1/4, which means comma denominator. Multiply by that fancy 1 again. So now I got 15 and 2/4 that I'll add another 1/4 to and get what?
15 3/4.
Good. So now I got this added in, and that gives me 15 and 3/4. But now what do I need to add? The 1/8. Which means, again, get your common denominator. So in this case, I'd have to multiply by another 2/2 to get 15 and 6/8, which adding that extra 8 gives me 15 and 7/8. Are you guys starting to see a pattern? What would the next one be if I added 1/16? Anybody want to guess?
15/16.
Yeah, very good. You notice that this one was 15 and 3/4. This one was 15 and 7/8. So when I add this, I'm going to have to double again and get 14 plus 1, which is 15/16. That's right. How about if I added 1/32? So the more and more I add, the closer and closer I get to what? Very good. Now, will I actually ever reach 16?
Probably not.
Yeah, not really. But we're going to get so darn close because remember, when does this end? If there's a dot, dot, dot. Never ends. So therefore, we're going to say that it is 16. But that's more that limit stuff and what it's approaching, like we talked with asymptotes in all the graphing that we did earlier on. All right, so with this, let me now show you this formula here and how it works. It's A1 over 1 minus R. And what did we say that the R was?
One half.
Very good. That 1/2, which means I will put that in there. And they gave us A1, which is 8. Now all I got to do is simplify this, which I know that this I can write as a different looking one. And I get 8 over 1 minus 1/2 is just 1/2. But do we like dividing by fractions? No, so we're going to have to multiply by that fancy one again of 2 over 2. Everybody see my 1 here? Why did I put this as 2 over 1? Because now that cancels and the whole bottom is just 1. And now I just have 8 times 2, which is what we saw we were approaching. But way nicer than doing all of that is this formula for an infinite. We just added numbers that never end, and that's pretty cool. Hold your applause until the end. You guys are all muted. Okay. Now, that's the end of that section. Of course, you guys are going to have to do other things with it. All right. But we're going to kind of change gears a little bit here and talk about these, what are called counting principles in 13.5. If you guys took Algebra 2 or Math 3 in high school, you may remember some of this stuff. They're called permutations and combinations. We want to figure out how many different ways we could possibly do some task, like order a pizza. And let's say that the pizza chain you went to had 10 toppings, but you had a coupon for just a large 3 topping. So out of those 10, you had to choose 3. And what we want to figure out is how many different ways that we can do that, because we're all splitting, or at least a few of us would be, right? Because that wouldn't be much pizza for all of us. So how do we attack this? Maybe you work for the company in the advertising sector, and you wanted to make sure that you, on your commercial, let everybody know that there's so many choices. Well, those are the things that we're going to discover in this section. Okay? So one process that we'll be talking about is aptly named, because what we do is just multiply. So however many choices there are, you will multiply each individual choice. So if you were getting dressed, right, or had to pick at a restaurant an appetizer, the main dish, and a dessert, and there were 3 of these, 5 of these, and 2 of these, how many different ways could you order your meal? Well, the multiplication principle says, if I have this choice, and this choice, and there's this many ways to do each, all I do is multiply them, and that would be 10 times 3. There would be 30 different ways to order your meal. It's that simple. So what I like to do is just draw blanks for each choice, each event that's going on, and then multiply the number of ways that I can do each to get the total number of ways to do that one thing. All right? A couple of keywords are and or. When you're asking yourself, do they want this and this? Then we're going to multiply. But if they want this or that, then we're going to add. Okay, so these are the types of things that you need to make sure that you're aware of. When it says and, we will multiply. When it says or, we will add. Okay, one of the ways that we're going to talk about this in other terms, and so that we can do things more quickly sometimes, is what is called a permutation. Okay, so permutations is another way to order objects, but permutations, order matters. Because if we were going back to that original problem, making a pizza, does it matter if you put the pepperoni or the sausage first or second? No. So order wouldn't matter, which means we're going to need another word and another formula for when order doesn't matter. And what is it called when you order a pizza and you have a bunch of different toppings, like 3, 4, however many? What do they call those types?
Combination.
So guess what we're going to call it when order doesn't matter? Combination. Okay, so that's again when order does not matter. We will use this thing called combinations. Now, why, you might be asking, is all of this stuff in this chapter? Well, remember, here's the formula for what are called permutations. And notice what is also in there that we talked about last week.
Factorials.
Very good. To emphasize it. Factorials, which remember means take whatever number that is and multiply every integer on down to 1. So the n is going to represent the number of things, okay, distinct or different objects that we're dealing with. R is going to be how many we're going to select. So if I wanted to take the 20 people in this class and I wanted to make a president of the math club, a vice president, and a secretary. Notice what was the key word that I said in between each one of those? And, which means?
Multiple.
Very good. So let's say that there are 20 students and we want to choose 3. How many different ways could I do that? Well, who could I choose for president? Obviously, we're going to stick with that one first because it's usually the most important. How many of the 20?
Choose all 20.
Yeah, just one. That's why there's only one blank for president, but I can choose any of the 20 people. And then I'd have to choose a vice president, which means how many choices do I have there?
19.
Now, good. Why did you go down one number?
Because there's already a president, so you can't choose them again.
Can't choose that person for all 3 spots, most likely, right? So order kind of matters in this case, right? And then obviously 18, we'd take that, we'd multiply those out and get how many different ways that we could do that. Now, does order matter? Would you rather be the president over the secretary? Well, if the answer is yes, and again, don't just take what you think, but does order matter if you're president versus vice president versus secretary? Yeah. Then order matters, which means we can set up a permutation. And what we're going to do is we're going to put the number of things on the left and the things that we're choosing on the right. So in this case, it would be a permutation, meaning order matters, and we have 20 people to choose from, and we're going to choose 3. Which means, according to this, we're going to put 20 factorial. Holy cow. We're definitely going to need a calculator, right? But watch this. What do we put on bottom?
20 minus 3.
And what is 20 minus 3?
17.
So look, you know that this means 20 times 19 times 18 times 17, 16, 15, 14, all the way on down to 1. And what does this mean?
17 to 1.
All the way down to 1. That's right. And since they're all multiplying on top and bottom, can we actually divide and cancel some stuff? That's right. So I'm going to go ahead and cancel all the 17, 16, 15, 14, 13, all the way on down with the 17, 16. And what's the only things that are going to be left?
The 3 or 20, 19, 18. Oh.
It's the
Hey.
same as if we were just drawing blanks over there. Now, here's the cherry on top. Because you can use either or, I don't care which. But here's the cherry. You actually have buttons on your calculator that if you just put this in to the calculator, it will do all of that with the push of a button. Okay, so make sure that you look for that by the end of today's lecture because that can save you some time. All right, so what happens if order doesn't matter though? What if I was just choosing 3 students to be a part of my math club? Well, now that changes things a bit. And how does it change things? Student 1, student 2, and student 3. Now does order matter?
No.
But I got to choose a student and then another and then another. And if we're still dealing with the 20 students and still choosing 3, but this time for a club, a math club or whatever, Alan's favorites, whatever you want to call it, what would be the next slot? Would I put 20?
No.
No, I can't have the same student if I'm trying to choose 3. So it would still be 19 and 18, but there's a problem there because that is the exact same as up here, isn't it? So what we're going to do is we're going to talk about how many different ways that I could rearrange those 3 people. And if I did that, then I'd have this on top and I'd have to divide. Get rid of the number of ways I can rearrange. I'm going to call them the chosen ones. And if I choose 3 people, how many different ways can I choose those 3 people? Well, I got to choose the first person. And how many people did I say I was going to choose total?
3.
So how many people can I choose first?
1. Oh.
Good. But I have 3 choices for that first blank. Very good. And then I need to choose the second person. Which, how many people are left?
Wouldn't it be 2 and 1?
Very good. 2, and then the last one of the 3. So there's actually how many different ways to choose 3 people?
Six.
Very good. Now, do you guys recognize how I could rewrite this rather than just putting 6?
3 factorial.
Very good. So if you notice, we'll get the same thing that we originally had, which is this. Does everybody see that? That is my permutations when order matters. But when order doesn't matter, we also have to divide and get rid of the number of ways that we're going to choose those people or objects or whatever we're dealing with. And that, my friends, is what is called a combination, or NCR. It's always going to be n factorial over n minus r factorial. But if order does not matter, then we will also divide by r factorial on the bottom. That's the difference between combinations and permutations. Okay? But there's one last thing that we want to talk about when dealing with these, and that is when we're rearranging stuff. But let's say Emily has an identical twin, and I cannot tell them apart. And that very well could be the truth. She may be sitting right there, and I can't tell. All right? And what if we had them as our 2 out of the 3? Well, now when I rearrange them, I'm not going to be able to tell if it was them. So the easiest way that we're going to talk about this and make sense of it is that if we had words where there are things that repeat, and I want to know how many different ways could I rearrange these letters, whether the word makes sense or not. How many different ways can I rearrange this? I'm coaching baseball, so I don't know why I said bad dad at baseball. Because there's some dads that like yell, you know. I'm just kidding. But just easy words that, let's start with just 3 letters, and then 2 that repeat, and then we'll get a little bit larger. How many different ways can I do this? Well, could I just draw 3 blanks for my 3 choices? How many different letters could I put here?
3.
Good. Any of the 3. What's the connecting word? What should I say then next? And then I need to choose another letter. And how many are remaining?
2.
And then there would only be 1 left. So rather than counting 1, 2, 3, 4, 5, 6, 7, 8, and drawing 8 blanks, how could I speed up this process? How many letters are there?
3.
And if we can't reuse them, then obviously it's going to end up being 3 factorial, or 6 different ways. And you could write out the entire, it's called sample space. You could write down every scenario. You could do BAD. And then switch it around as BDA. And then start with A and go ABD. And then ADB. Switch those. And then you could start with the D and go AB. Or then you could go DBA. And are there any other ways that I could rearrange these? I started with A and then switched these 2. I started with B and then switched these 2. And I started with D and switched these 2. There's no other ways to rearrange these. And so you can see that this works. However, how many different ways would I have for dad then? Watch this, guys. I don't know if you guys believe me. I'll put my hands up. I'm going to switch the D's. Ready? Did you see it? It happened so fast you probably didn't see it, but I just switched the D's. Emily liked that one. No, you can't tell, right? Unless you actually put this as D1 and D2. Then if I switched them, then you'd say this is D2, A, and then D1. But we're not going to label the D's differently. or the B's or the L's or the A's or any of that stuff. So what we need to make sure is that we know that just because you have 3 letters does not mean that you're going to automatically just have 3 factorial ways to do it. There's going to be more or less.
Less.
Which means we need to divide the number of ways that we can rearrange, in this case, the 2 things that repeat. And we know if there are 3 things, and they're all different, then there are this many ways. So if there are 2 things, how many ways could we rearrange those? Now, obviously, I don't need the factorial because it's just 2 times 1, which is 2, but I'm trying to prove a point. Because I can get crazy with you all and say, do this. And tell me how many different ways we can rearrange the letters in Mississippi. That'd be fun, huh? But notice the 2 factorial will cancel with the 2 factorial, so we're only left with 3. It is cut in half because of those 2. The only thing I can do is rearrange the A to be at the front and then rearrange the A to be at the end. Those are the only 3. There's my sample space. But I don't want to write out all of the options for this, because that has a lot more letters in it, doesn't it? So what is the pattern? Can you guys tell me? How would we set this up? If those were all different, then we know we would have how many slots?
8.
8.
So that we will always put whatever's up there factorial for how many different and distinct things. But unfortunately, there are some things that repeat. And what are repeating?
B, A, and L.
Good. Now, did you guys hear what Brianna said in between them? She said B. What was the connecting word? What was the connecting word, Brianna? I'm sorry.
It was and.
So that means how many different ways can I rearrange the B's? How many of them are there?
2.
And then I'm going to have what?
2 A's.
2 A's that I could switch and it wouldn't give me anything new. And there's 2 factorial ways to do that. And then there's what?
2 L's.
And be careful, ladies and gents, when we multiply 2 factorial, 2 factorial, and 2 factorial, does that give you 8 factorial? Would that cancel out with this and we just get one way to write baseball? It's always baseball.
No.
Definitely not.
Right.
So remember, 2 factorial simply means 2 times 1, 2 times 1, and 2 times 1. Which means we actually have what? We don't need those. It's 2 times 2 times 2, which is 8. And what can I actually cancel with that 8 on bottom now? The 8 on top. And I would only be left with 7 factorial then. So you could just punch that into your calculator. Done. Right? So here is the formula if you wanted to see it. The number of things that you have, factorial, will always be what goes on top. But however many things repeat, factorial will be what's on bottom. Right? So that is the last thing for that section. And here comes one of my favorite sections of the class. It's lots of fun. We get to take, and it's all doing the same thing, okay? It's all we're doing are what are called binomial expansions. Binomial, break down the word. Bi meaning two, nomial meaning names or terms. So we're dealing with two-term expressions. And what they want us to do is expand a two-term expression. So if I have two terms, anything plus anything else to the zero, first, second, third, fourth, should we be able to do this? Yes. Do we really want to? No. So what we're going to do is find a shortcut. All right. So watch this. This is everything in this entire section. This last one here for chapter 13. And all we're going to do is learn two different techniques on how to accomplish this goal. So bear with me. There is a reason I'm doing what I'm doing. You just may not see it until the end. What is anything to the zero power, everyone?
1.
Good. What is anything to the first?
Itself.
Those are easy. And you may even know anything squared by now. Because remember, we did that a lot when we were doing stuff like this, the difference quotient. And we had, you know, y equals x squared plus 3x minus 5 or something like that. That you guys actually just did one on your test. I didn't even give you the end. It was just something like this. And you had to take that binomial and square it. What is anything squared? For time's sake, it's this. Now, what would I have to do in order to find the cube or the fourth or the fifth or any other binomial to a power? I'd have to take the previous thing and multiply it by one more. So it would be a plus b times a plus b. And we got this. So now I can take this, which is equivalent to that, and multiply by one more, a plus b. So I'm just going to do this off to the side one more time. And guys, watch what happens. What is the process that I'm going to be using? What is that called?
Distribution.
Good, and that's what a lot of people will say, Emily, is foiling. But Anthony is actually correct, which is why I tried to give you the hint. It's actually distributing. Foiling only works when it's first, outer, inner, and last. When we have a binomial times another binomial, then I can do the first, then I can do the outer, then I can do the inner, and then I can do those last ones. But this has more than a first, outer, inner, and last, doesn't it? So that's why I like to always just use distributing, because it always works. And what am I going to be distributing to each and every one of those?
An A.
It's Mr. A to you. Very good. It's an A, which means every single one of these is going to increase by an A. So that's going to give me a cubed plus 2a squared b plus an ab squared. Does that make sense? Because what am I going to do next?
Distribute the B.
And what is that going to do to each one of these now? It's going to give them an extra b. Now watch, I'm going to go down one over one, and I'm going to put it right under this term, because when I distribute the b to the a squared, I get a squared b if I keep it alphabetical, right? And a squared times a b. Then the b times this will give me 2ab squareds plus a b times the last thing will give me a b cubed. And when I add all of that up, I have my like terms stacked. I have 2 there and 1 there. I'm adding together to get 3 a squared b's. Remember, when you add, the only thing that should change is the quantity, how many you have. Okay, not what you have. Here I have 1 ab squared. Here I have 2. So together I have 3 of those. And then just a b cubed by itself. So now this one is an a cubed plus 3a squared b plus 3ab squared plus b cubed. Now again, we could do the next one and take this and multiply it all by another a plus b to get our 4, since this was our 3. But I am starting to recognize patterns. Are you guys? What do I know is going to end up on my ends? It's going to be an a to the 4th and a b to the 4th. Notice this cube was actually with every term. Obviously with the circles, but can you see the boxes that I put? That's 2 and 1. That's 1 and 2. So every single one of those had a degree for each of my terms of 3. Now the coefficients are a different story. We'll talk about those. But who can tell me what the next thing should be? Something AB plus something AB plus something AB plus that. And notice how many terms we end up having. They're all start as binomials, but when it was raised to the 0, I had 1 term. When it was raised to the first, 2 terms. When it was raised to the second, 3 terms. To the third, 1, 2, 3, 4 terms. So that's why for this one, I anticipated 1, 2, 3, 4, 5 terms, sticking with that pattern. Does everybody see that? Also notice a to the 1st, b to the 1st. A squared, b squared, ab. All adding up to the 2nd. Look at this one, 3, 3, 3, and 3. So what do we know each and every one of these should add up to be?
4.
And if you notice, there's also a pattern with the a's. It goes 3, 2, 1, and then how many a's here? 0. And then look at the b's going the other direction. 3, 2, 1, and 0. Well, then help me out, guys. What should we know that my a in my second term is going to be if it starts at 4?
3,
Then what?
2,
Then what?
1.
And then no a. And if I read it right to left and I start with the b to the 4th, what do I know the next one should be?
3rd.
3, 2, 1, and 0. All we have to figure out are what these coefficients are. And can you guys see the design that it's starting to make? There's another French mathematician. His name was actually, his first name's so cool, I always have to say it. Blaise Pascal. And you guys may have heard of this before. It's called Pascal's triangle. And what Pascal's triangle allows us to find are, for binomial expansions, all of the coefficients. And all we're going to do is start with ones on the outsides, as you can see. But how do we find on our birthday cake here, with all the ones and all the candles on the outside, how are we going to find the best part of the cake, the inside, the filling? We'll notice some more patterns. 1 and 1 together make 2. 1 and 2 together make 3. So if this is a 1 and this is a 3, what do you think is going to go here?
4.
You got it. What's going to go to the next term? What would its coefficient be? And so on. So if we wanted to do a plus b to the 5th, we should be able to do it very quickly based off of all of these patterns that Blaise Pascal actually discovered. Okay, so that is one technique in doing this, but as you can see, it can take some time. So we're going to learn some of these methods so that we don't have to multiply it all out to do something like this, because we will have much higher powers than just 4. And we will have more than just a plus b or x plus y in there. Okay? So Pascal's triangle, we're going to start with that. Let's make sure that we can build it. It's obviously going to start with ones. And I'm just going to keep expanding out because we know that that's what happens, however far I want to take it. But remember, what is going to go in the middle? How do we find all that? You simply take any 2 and put the sum in the middle. Take any 2, put the sum in the middle. And so on and so forth. Okay, so those 2 would be 2, 3 and 3, 4, 6, 4, 5, 10, 10, 5. And what do all of these represent in this Pascal's triangle? And talk about patterns, guys. Obviously, you can see the pattern of the ones, but look at the next diagonal. Either direction. Look at the next diagonal and its pattern. Increase by 2, increase by 3, increase by 4. All kinds of fun stuff that people have tried to find more applications of Pascal's triangle for. All right? So help me out. What would the next one be? What would the next line be? Make sure that you guys can do it. What did you guys get? What is that next line?
6, 15, 20, 15, and 6.
Yeah, notice that it's also symmetrical, right? It's symmetrical. Same that way as it is this way. Okay? Same that way as it is this way, which is nice because if we get half of it, then we know the other half is just repetitive, the other direction. So if I find this, and I know these, then I know the next one's going to be 15. The next one would have been 6, and we got our 1s always on the ends. Very good. So remember, how can you always tell which row you need to take it out to? Well, it's very simple. All you got to make sure is that you know that whatever exponent is that you're dealing with for that binomial expansion, you look 1 to the right, 1 to the right, 1 to the right, and that will tell you what power it is. So notice there's nothing here, that's why it's to the 0. This would be to the first. This would be to the second, to the third, to the fourth, and so on. Okay? So of course we'll do an example to make sure that we can apply that Pascal's triangle, but I wanted to make sure that I go over it, how to build it, and what it represents. Unfortunately, it only gives us the coefficients. But remember, we saw a pattern with the A's and the B's for each of these as well. Okay? Now there is another one called the binomial theorem, but I think it's uglier and more involved than it's worth. So I'm going to kind of explain how that one plays in as well before we actually do an example. Actually, let's do the example and then I'll explain it. Okay? So what do I know? How many terms will there be for this particular one? Since it's raised to the 6, how many terms will I have?
7 terms.
Very good. So I'm going to draw 7 blanks to represent each of those. What can I fill in of those blanks already? What do we definitely know?
X to the 6 and Y to the 6.
Good. My ends will always end with 1 or start with 1, and then I will have X to the 6 at the beginning, Y to the 6 at the end. And what are all the other ones going to be made up of?
Powers that add up to 6.
Very good. Powers on our X's and Y's, those A and B terms. So I know that all the rest of these will have those in them. And Brianna, what do we know that we're going to start with? Whatever the power is that we're raising it to. And since the one on the left was the X, I know I'm going to go left to right and do what to all of those?
Decrease, like get lower.
Good. So it will be 5, 4, 3, 2, 1, and then X to the 0, which I'm not even going to put. Then what am I going to do with the Y's from right to left?
The same thing.
5, 4, 3, 2, 1, and then 0. And notice that whatever that power is, all of these add up to be that thing. So all we have to do to finish, guys, is know what?
The coefficients.
That's right. The coefficients, which we already know this and this are going to be 1 always. So all we have to figure out are 1, 2, 3. And then we actually have these, don't we? Because these will pair up, these will pair up, and then this is by itself because we know, based on Pascal's triangle, that it's symmetrical. And didn't we already do to the 6th power? Then we should be done. Now notice another one that you should know other than just the ends are the next 2 slots, because those will always be whatever that power is. So I know that this has to be a 6, therefore this has to be a 6. But what were the other ones? 15, 20, and 15. And guess what you guys just did in a matter of a few minutes. And again, it'll be faster. I'm just explaining every step and making sure that you guys understand what goes where. You just raised x plus y times itself six times, which you would have had to FOIL, distribute all of that, and then get this one and do the same, and then the same, and then ugh. This is beautiful. Way faster. All I ask that you do is after you've done that, take away the parentheses and give me the final answer. X to the 6 plus 6x to the 5th y plus 15x to the 4th y squared plus 20x cubed y cubed plus 15x squared y to the 4th, 6xy to the 5th, plus y to the 6th. And we did all of that in a matter of seconds. That's pretty cool. Now, let me add in the binomial theorem, but I'm going to give you my own adaptation of it. Okay, before we do this next example, I want to show you guys how you can come up with these without having to build this all the way on down to that 7th row, because they were counting the 0 power, right? If you don't want to do this, here's an alternative method, okay? You still would go back and start it the same way we did with the xy's. But here's the cool thing. We can use our permutation style format. And guess what? It's very simple. All you have to do is always put whatever the power is on top of every one of these. That will not change. Okay? But what we will divide by in order to get these coefficients is whatever the exponents are. Each of them multiplied together. So I will simply just take 5 factorial times 1 factorial, 4 factorial times 2 factorial, 3 and 3, 2 and 4, which I already did, so I'm not going to do this again, and 1 and 5, which I already did. I'm not going to do this again. I'm just going to take whatever these are and plug them in. So I actually only have to do half the work. But make sure that you understand factorials, because what is that going to force us to do? Bunch of multiplying, dividing, unless you know how factorials work. Because what is going to happen to a 5 factorial dividing into a 6 factorial?
It's gonna leave us. Wait, never mind.
No, you're right. The 5, 4, 3, 2, 1 will cancel with the 5, 4, 3, 2, 1, and we'll only be left with 6. How about the next one? The 6 factorial over the 4 and 2 factorial. Which ones can I cancel easily? How about the 4, 3, 2, 1? That's the bigger one. That gets rid of the 4, 3, 2, 1 up there. So I'm still left with the 6 times 5 over 2 times 1. And I know that goes into this, so I get 15. And if that's 15, then since this is the same two things, then this is also 15. You guys getting it? So then this one up here, I'm going to cancel one of my 3, 2, 1s. So I'm still going to be left with 5 times 4, but the 3, 2, 1 canceled, but I still have a 3, 2, 1 down here. And what is 3 times 2?
6.
Well, then I get to cancel a 6. And what's the only thing that's left that's not a 1? So this is an alternative method, okay, called the binomial theorem. Where we take the n factorial of a plus b to the n, and we divide it by r factorial s factorial, where r and s are going to be these. Exponents. Okay, so that is my adaptation for the binomial theorem and the what are called coefficients. We know how to find all the other stuff. We found that pattern. So let's do one more together just to make sure that you get it, and then we'll wrap up today with one final example to see if you guys actually understand this. So if it's to the 5th, how many terms am I going to have?
6 terms.
1, 2, 3, 4, 5. I'm going to draw 6 blanks. What are they all going to be made up of?
A and B.
Now careful, when you say A and B, remember I generalized it with A and B. My first term is A, so that's the same, but what is my second term? Is it just B?
It's 2B.
Close.
Negative 2b.
I got to keep the sign that's with it. Okay, we didn't need to do that with the positives, so that's why I wanted to do another example. It's negative 2b for every single one of these. Oops. Now, if you think this takes a long time, I challenge you to raise this to the 5th and multiply it times itself 5 times and not make a mistake. Every year in high school when I would teach this, and even in college sometimes if we had time, I would ask one particular student to race me. And I would take the time and I would still explain everything that we've been doing, and I'd let them multiply that out 5 times. And guess what? Without fail, I would either beat them or I would be correct and they were not. So this, although it takes a while, is much faster than actually expanding that out on your own. Okay? Now, before I do anything with the coefficients, I'm going to go ahead and get my exponents. And because it starts with a 5, I will start on the left with a 5 and then drop 1 for each. 3, 2, 1, 0. And then I'll go back from right to left. 5, 4, 3, 2, 1, and 0. And we know anything to the 0 just becomes a 1. So that's why some people won't even write those. And we also know our coefficients of those will be 1. And what other one should you be able to fill in? My second term, because we knew that each of these matched up with the exponent, I should know those as well. So that means I also should know that this is what?
5.
And if that's 5, we should also know that the second term from the right will also be 5. So we really only need to find this one. And if I can find this one, then I know because it shares these, it's going to be the same. So am I going to build out Pascal's triangle to find this? No way. I'm just going to use the 5 factorial over 3 times 2 factorial to find it. And once I know that, then I know this will be the same. So help me out. What would that be?
10.
Good, because the 3, 2, 1 would cancel with that. So I'd be left with 5 times 4, but I still have over 2, which I know can cancel with that. And I just get 10. Done. All I got to do is simplify this mess. And there is a lot more simplifying when one of two things happens. You have coefficients with your A and your B term, and especially when there is a negative. So let's make sure that we can simplify, and then we'll move on to the last thing, and then we're done for today. This, we already simplified. We knew it was a 1. We knew this is a 1. So it's A to the 5th. There's my first term. But be careful. The next thing has a 5 times A to the 4th times a negative 2B. And since all of this is multiplied together, there are some things that we can multiply that are alike, aren't there? Such as what?
The 5 and negative 2.
Good. What is 5 times negative 2?
Negative 10.
Times A to the 4th times B is A to the 4th B. Excellent, Heather. That's what our second term is. Help me out. What's the next one then? Remember your order of operations. You got to do parentheses. Nothing to do in each of the parentheses. Next are exponents. When I cube A, I get A cubed. Not anything special there. But when I square a negative 2, what does it become?
Positive 4.
So I like to write it underneath before I move on. Now I can see I can multiply those, and I get positive 40 times the A cubed times the B squared. And notice all of my powers are still adding up to the 5 as it should. Okay, so help me out. What would the next one be? Since it's a negative to the odd, it would be negative. What is 2 cubed?
Negative 8.
Good. So multiplying that out, I get negative what?
80. 80A squared B cubed.
Excellent. Now you guys are starting to get it. 5A. This would be, what's 2 to the 4th? That's just another 2, so it would be what? 16. And what is 16 times 5?
80.
Good. 5 times 10 is 50. 5 times 6 is 30. So together, 80 in A, B to the 4th. And then the last one, again, be careful. Everything's 1s but this. It is also going to be negative. And what is 2 to the 5th?
32.
And my friends, I guarantee you that is faster and safer than multiplying that whole thing out, foiling, distributing each time. Notice when there was a negative here, what did my signs do?
Started alternating.
That's right. That's why a lot of this stuff, because there are factorials, alternating, patterns, all get thrown into this chapter as well. Okay, so here's your last task. Let's see if you guys can do that. And we are done. We'll wrap it up today. I only want the 7th term. Does that mean you have to build out all of the terms? How many would there be, by the way?
11.
Good. So I'm just going to draw little dashes to represent each one of my blanks. But then for the 7th one, 1, 2, 3, 4, 5, 6, 7th term, 8, 9, 10, 11, that's the only one I want. And what do I know it's going to be made up of?
3x and negative y.
And if I can find the exponents, then can't I find, using that adaptation of the binomial theorem I showed you guys, shouldn't I be able to find the coefficient? What is it always going to start as on top?
10 factorial.
Very good. All we need to figure out is what this is and what this is so that we can put those down there and have them here, and then we'll finish. Now, is it closer to the right or is it closer to the left?
To
The right.
Then I would start with the right and I would put my exponents. What do I know would go here?
Negative y. To the
Good.
10th.
10, 9, 8, 7. So what?
6.
6, which means I know I'll put that under there. And since we know that this sum always has to equal that, we don't need to count from the other side. We know this has to be a what?
A 4.
And if that's a 4, we throw the 4 down there, simplify, and you're done. Very good. 6 cancels with all the 6 up there, so I'd have 10, 9, 8 to 7, 4, 3, 2 still down there. So with that, a 2 and a 4 cancel with the 8 and the 3 with the 9. So I just get 3 times 7, which is 21 times 10, which is 210. That would be my coefficient, but I still have to do this stuff, which I know 3 to the 4th. I know 3 times 3 is 9. 3 times 3 is 9. So there's my 4 3's. 9 times 9 is 81. X to the 4th. And since it's a negative raised to an even, it would become positive. And now I will use a calculator to multiply that out, get my final answer, and I'm done. Anybody get it?
$17,010.
Ugh. Glad I didn't have to do that. But look, we were able to find if this was multiplied out times itself 10 times, that final product, all 11 of them, we're able to find the 7th term without doing much. All right, pretty cool. Hopefully you guys got most of that today. I know I threw a lot at you, but hang in there, practice this stuff, and if you need help, come see me or our tutor.